Hello and welcome back to the CCENT journey with me, Ryan. In this next section, we're going to continue with the routing part of the ICND1 or CCENT, and we're going to talk about the routing protocol that we need to understand in more depth and do how to configure, troubleshoot and verify, which is RIP, the Routing Information Protocol. For those who don't know, you can contact me here on YouTube, on LinkedIn or Twitter. So first of all, we need to talk about RIP as an overview, and we need to jot down some stuff that we need to remember about RIP and why it's important to remember it. So first of all, what does RIP stand for? It stands for the Routing Information Protocol. Now we've already gone through a bunch of videos to discuss why routing is needed and dynamic versus static routing, and we know from those videos that RIP is a dynamic routing protocol. IGP. RIP is part of an IGP. Remember, we had two categories. We had IGP, which stands for Interior Gateway Protocol, and this is where things like RIP, OSPF, EIGRP, a bunch of protocols sit. And we also have EGP, the Exterior Gateway Protocol, which is where BGP sits. And we said in the previous videos that EGP is between autonomous systems, or sometimes referred to as administrative controls, and IGP is within it. So this means that when we configure RIP, OSPF or EIGRP, we would configure it within a network, and then we would link multiple networks together using BGP, or multiple administrative domains together. For example, maybe there's a large company that's global, worldwide, and each continent or country has their own method of doing things, and they have their own IGPs, and they link back into the larger company using some kind of BGP. RIP is considered distance vector. There are different types of categories routing protocols fall inside. RIP falls into what we call distance vector. We've also got something called link state, which is where things like ISIS and OSPF falls into. We've also got something called path vector, which is where our BGP falls into. And we've also got something called either advanced distance vector or sometimes called hybrid. And this is where our EIGRP falls into. Now we need to be aware of link state and the fact that OSPF fall inside it, and we need to be aware that RIP falls into distance vector, and arguably so does EIGRP. And I say arguably, it's because depending on where you actually read about EIGRP, you may hear it being referred to as a hybrid protocol or an advanced distance vector protocol. And when you get into your second part of your studies towards the CCNA and you start to learn about the Enhanced Interior Gateway Routing Protocol, EIGRP, you start to realize why it's referred to as an advanced distance vector or hybrid as opposed to just a standard distance vector. But if you were asked a question, is EIGRP distance vector, and there's no other better option like advanced or hybrid, then pick distance vector. Make sure you're aware of link state. Make sure that, particularly OSPF, you're aware that that is a link state protocol. I wouldn't worry about the path vector at all, because I don't even think BGP is even remotely discussed in the CCENT. It may not even be discussed in the CCNA. But it's good to understand if it comes in as an EGP versus an IGP, because it helps to have a view of the big picture when we look about how networking works on the internet or between organizations. So what is distance vector then? So distance vector is one of the categories that we put our routing protocols into. We've just seen the others, which are link state, hybrid and advanced distance vector, and path vector. But distance vector is, to an extent, kind of what we already know about routing so far. Let's say we have three routers all connected together in some kind of daisy chain environment here. And off the back of this router, let's have a /24. Well, what we do know is when this /24 is advertised into, let's say, RIP, and RIP is running on all of these links, then we know that this router will put it inside its routing table, and then once it does that, it then takes its entire routing table, passes it to the neighbor installs it in its routing table, picks it up, passes it to the router downstream, and again this person installs it in their routing table. And what we have is we have full reachability. Each router knows how to reach the /24. We got the router on the far left will go to the middle router, and the middle router will go to the far right router. But the problem we have here is we only know what our neighbors tell us. The router on the left has no direct visibility of the router on the far right. And you may be thinking, well, who cares? Why would it need full visibility? Well, let's say this /24 goes down. What we need to do is wait for it to be removed from the routing table, wait for the next update of the routing table to be sent to the middle router, which now excludes that /24. We would need to wait for this router to remove it from its routing table and then pass it on to finally this route to then be removed. But in the meantime, traffic is still trying to get sent through the middle router to the /24, and of course it's being dropped because no traffic can actually reach that destination because it's no longer valid. And this whole process and this time it takes to do this process is it's time consuming, it's very inefficient, and it can cause lots of problems with loops. So there are some very, very basic rules like split horizon and count to infinity and poison reverse that are used to help prevent these scenarios and speed up the routing process. Just to elaborate on that routing loop example, let's say that we label them up, router 1, router 2, router 3. As router 1 tells router 2 that the /24 is no longer available, router 2 finally removes it from its routing table, and just as it removes it, router 3 tells router 2, hey router 2, if you want to get to the /24 over here, you can go through me. But what router 2 doesn't know, because remember it only knows what the neighbor tells it, is that /24 is actually back on itself. So router 2 will then say, brilliant, I'll use router 3 to get to the /24, and router 3 is obviously using the router 2 to get to the /24. And this is how a loop will occur, and that loop will need to be fixed by other distance vector features. So what about then, instead of using RIP, which we said was a distance vector, we had something like OSPF, which is actually link state. Well, in this scenario, what would happen is as soon as that /24 is lost, router 3, because it's link state and it's running OSPF, it has full visibility of the entire network because it has full visibility of all the links and the state of the links. So router 3 knows that router 1 is behind router 2. So if the link over here was lost, it knows not to route back to router 2, but maybe find an alternative path that router 2 may or may not know about in order to reach router 1. Because when we talk about link state, we have the entire map of the network, not just what our neighbor tells us. And the benefit of having the entire network is, of course, like you've seen, we can take different paths and we know not to make certain decisions. However, the next thought that will probably pop into your head is, well, why do we ever use distance vector to begin with? Why don't we just use link state everywhere? Well, different protocols again have different design benefits. Because of the basic design of distance vector being on a per hop basis, if you like, it means that the hierarchy can be anything we wish it to be. And I'm not going to go into details of that because it's outside the scope of the CCENT, but you'll come to find and understand that different protocols have different benefits. Some people prefer distance vector versus link state. Some people prefer link state over distance vector. But it's important to understand at the CCENT level the difference between distance vector and link state, and to know where OSPF, RIP and EIGRP sit inside that, and then to also know the different ADs and metrics for those three protocols. But more importantly, we need to know RIP in more detail. We need to know that it's an IGP. We need to know a bunch of information about how to configure, verify, and do some basic troubleshooting. So there are two versions of RIP. There is version 1 and version 2. Now the exam only focuses on version 2. Now just so you know, version 1 was a classful version of RIP 3.2, which of course is classless. So we've talked very extensively about the history of subnetting and the history of IP addressing, where we had our different classes like Class A, Class B, Class C, versus when we go to CIDR or classless, where we actually have any sort of subnetting or any networking that we wish. Well, version 2 supports the classless approach, and of course our networks today are built classless and not built classful. There are some other minor differences, like for example RIP version 1 was broadcast, whereas RIP version 2 is multicast, and we'll get into understanding how that's different in RIP in a moment. But we already know, again from previous videos, that broadcast is to anyone. So if I've got a switch and that switch has a PC and let's say two routers connected, and the router sends a RIP update onto the wire, because it's a broadcast traffic, both the router over here and the PC will receive that traffic. The NIC card on the PC will accept it, but of course the process of RIP is not running on the actual device, so it would be dropped. But there'd be a waste of network resource and CPU utilization on the device in order to accept that traffic and to process it. Well, when we think about multicast, each device queries or essentially ask the switch to be part of that multicast, and because of that it's not sent everywhere. It's only sent out the ports that actually require it. So we're left with normally a more efficient method of having updates to the devices that require them and not to devices that don't. Multicast is one to many, whereas broadcast is one to all. Now something we have talked about is the administrative distance, the AD. Now RIP comes in with an AD of 120, and remember the lower is better. We've again talked quite a lot about route selection. We said that if a router has multiple paths to a particular subnet or network, it will prefer the longest match first, and then after the longest match it will pick the administrative distance, which is lower, and then it will look at the metric if there are multiple paths with the same administrative distance. And in this case RIP uses what we call hop count as a metric. So this means regardless of the underlying throughput or the capability of the circuit, it's simply based on how many layer 3 hops are there to the final destination. So that means that if we had, let's say, a PC that connects to a router and it has, let's say, a few paths to get to the destination, and this is, let's say, 1 meg, whereas these are 10 gigs. As far as RIP is concerned, the best path would be to use the 1 meg link, and traffic will traverse this way simply because RIP uses hop count. So a key thing that we need to remember, admin value of 120. We need to know that metric for RIP is also the hop count. In my previous videos I talked about the OSPF AD being 110 and the metric being something we called cost, and ERGRP being the AD of 90, and confusingly enough using a metric called distance. Might be wise to also remember this. I'm not sure it's going to be on the exam, it's certainly not on the blueprint, but they may slip a question in regarding the AD values. So make sure you remember that. Next thing is the routing updates. They are every 30 seconds. It's the entire routing table. So if I have, again, let's say 3 routers in a row, this router here had a bunch of different /24s off the back here. Even though they don't change, every 30 seconds, this router's entire routing table is given to this router. This router will pass that information and create its routing table, and then pass it downstream and upstream, and eventually everyone will have the stable and hopefully correct routing table for end-to-end connectivity. But of course, as your network scales and more networks are added to it, more subnets are added, then you need to, of course, put in consideration that time the updates are even sent, the next update will be on its way. So there are things that we can do to help optimize RIP by using things like summarization, but that's outside the scope for the CCENT. In fact, the blueprint itself even outlines that it's outside the scope of the blueprint. What else is there to know about routing updates? Well, it uses UDP port 520. So what does that actually mean then? Well, if we have a think about what the RIP packet would look like, we know that it uses UDP, and we know that UDP is a layer 4 protocol, which means it works at the transport layer. So the way it would essentially work we would have a RIP header, and inside this RIP header will be basically a bunch of routes, which would be the entire routing table, and then that would be carried on UDP with the port of 520. We would obviously have the IP header then, and the destination IP header would be this multicast address of 224.0.0.9, and that is something that, again, unfortunately, you would need to remember. And then that would be sent to, obviously, an Ethernet header, which is where our MAC address is populated, and then it will go out onto the wire. So this is obviously our layer 2 as far as the OSI model is concerned. Here's our layer 1, 3, 4, and then upwards we just call this the upper layers. Now, something we've not talked about yet, and there will be separate videos towards the end of the course, is IPv6. Now, for now, what I would say is make sure you just remember this number, but this is actually an IPv6 address, and it's a multicast version of an IPv6 address. So multicast in IPv6 works just like we know about multicast in IPv4. The only difference is of course the addressing scheme is different. So 224.0.0.9 goes to FF02::9. And when we get into understanding IPv6 in more detail, we'll go over what the colons actually mean, what FF actually means, and so forth. But for now, let's just remember that FF02::9 is the IPv6 equivalent of the IPv4 multicast address 224.0.0.9. So before we get into actually configuring RIP, let's have a discussion around the commands that are required to get it up and working from a CCENT perspective. Now, first of all, we need to go into global config, and we need to type in router RIP. And this is also how you enable other protocols like OSPF, BGP, and so forth. But again, RIP is only the protocol that we need to worry about at the CCENT. We then need to type in two very important commands. We've got to type in version 2. So this makes it, as I said before, a classless protocol. So in the RIP update between routers, you'll notice that when you type in version 2, that update becomes a multicast to the 224.0.0.9, and it also has a subnet mask inside the packet. Whereas if it's not version 2, it's version 1, and most devices are version 1 by default, then you'll see that the update itself does not have a subnet mask inside the update. therefore it has to be class full. We also type this word no auto summary. Now auto summary is this very annoying feature where it kind of tries to help itself out by summarizing multiple routes. So to give you an example of the auto summary, let's say we have up here a router, and that router connects to the 10.1.1.0/24 network, and then it connects downstream here to this router, and then another router down here, and off the back of this router there's 10.1.2.0/24, and then between these two links here we have some kind of /30. We don't really kind of care what it is for this example. Now what we have is the 10.1.1.0 be advertised down here, and we'll turn on version 2, so the subnet mask as a /24 is included, and same is true here. This is also advertised, and we'll turn on version 2, so again the /24 is also advertised. Now on this router what we'll do is we'll still turn on version 2, but we're going to turn off the auto summary by typing auto summary instead of putting the no in front of it. So now what's going to happen is this router is going to try and be clever, and it's going to say I'm receiving the 10 network. The 10 is a class A, so I'm going to summarize, and I'm going to summarize it to 10.0.0.0/8, and since I'm receiving a 10 network on this interface and a 10 network on this interface, then I will say when it's in my routing table, if you want to get to the 10.0.0.8, you could go this way, or you could go this way. But that's no good to us, because now you have what we call a discontiguous network. Because what actually is happening is you have the 10.1.1.0/24, which is a completely different subnet to the 10.1.2.0/24, but the router in the middle is trying to be clever by auto summarizing those 10 networks to a /8 and then having it reachable out of both interfaces. You're going to have all sorts of problems where one packet may go this way, another may go that way, they may low balance, but you're going to get packet loss or no connectivity altogether. So in order to fix this, we would turn off the no auto summary to stop it from summarizing from a /24 to a /8, and in turn it will then know that that correct /24 network is reachable only out of this interface, and the same is true with the /24 down the bottom. So even though version 2 is enabled, and even though the subnet mask is sent in the updates, auto summary will still try to summarize it down to the classful boundary. So if it's anything in the class A, it will try to summarize it to a /8. If it's in a class B, it will try to summarize it to a /16 and so forth. So go in Packet Tracer, have a play with this discontiguous network, and in the next video we'll actually build a discontiguous network and look at the problems that we experience with it. So let's have a chat about these network statements. Now we've talked about the global setting, version 2, and the auto summary and what it does, and we said that we need to make sure it's no auto summary so it doesn't do that summarization. Now what the network statement does is the network statement says go find an interface that matches the network statement and turn the RIP process on within that interface. So for example, if I had a router and off that router, let's say I had fast Ethernet 00 and it was the 10.1.1.1/24 network. Well, when I type in the 10.1.1.0, this interface is matching that network statement. As such, RIP gets turned on that interface. So now RIP traffic is sent out of it, and any other interface that I may have already had RIP turned on, then this actual network also gets sent out of that process. So the network statement matches an interface and turns that RIP process on for that interface. And it's matching it against this IP address. But turning it on does two things. It sends out the RIP updates and it puts the subnet, or the network if you like, into the RIP process. Now, what's interesting with the network statements with RIP is if you were to type this in, the actual output of that would look like this. And you can see what's happened is all of these 10 ranges has been put back to its classful boundary of 10,000. The 172s have also been put back to its classful boundary. Now, this does not mean that it's now RIP running as classful. This is still a classless protocol because we have the version 2, and it's still not doing any summarization because we've turned it off. All this means is the network statements are collapsed to a classful, and it means that all of the 10 network is enabled. So the downside to this is, let's say we had a router and we had the 3 interfaces. Let's say one's 10, 1, 1, 0, and that's a /24. One's 10, 1, 2, 0, and that's also a /24, and 10, 1, 3, 0, /24. Well, at the CCENT level, what you don't get told is how would you only enable the RIP process for 2 interfaces and not the third, because we can see from doing the network statement that the 10 will match all 3 interfaces, therefore all 3 interfaces will be put inside the RIP process. So typing out the long-handed way will simply get collapsed to the short-handed way, and the outcome of that would be all the interfaces with the 10 as the first octet will be enabled for RIP. And that's something you might not want, and that's outside the scope of the CCENT. But for those that are interested, we would use something called passive interfaces as one of the workarounds to prevent certain interfaces sending out RIP updates. Okay, so that's all we've got time for this lesson. In the next lesson, we will go over the verification commands for RIP and actually jump into Packet Tracer and have a look at the configuration hands-on. So some of the things that we need to make sure that we understand and things that we've covered. Make sure you know what RIP stands for. It stands for the Routing Information Protocol. Pretty straightforward. We need to make sure we know the AD, which I said already is 120. We need to make sure that we remember the metric is based on hop count, not based on how fast the links are. We need to remember the multicast address, which is that 224.0.0.9, and the port number, which is the UDP port 520. We need to remember the basic configuration command. So remember that we do the no auto summary and version 2, plus the caveat with the network statements. We can type in a very specific network statement, but it will always go back to the classful boundary. Something I've put here was to understand the AD and metric of OSPF and EIGRP. Now, this I'm not too sure on because it's outside of the scope, but doing some CCENT test papers myself, I have seen questions like, what is the AD of RIP? What is the AD of OSPF? And they're really basic numbers. You might as well just remember them. So there's no harm in doing that. A lot of people don't stop at the CCENT anyway, and they go for the CCNA. And of course, in the ICND2, OSPF and EIGRP is talked about in more depth. And kind of one of the most important parts is make sure you understand what we're trying to achieve with RIP. It's a dynamic routing protocol. It allows routing to take place. Make sure you understand why routing is needed, what's the benefits of static versus dynamic, and why we might put dynamic in a network environment versus static. I hope this video has been informative. I'd like to thank you for viewing, and if it has been, please do like and subscribe.